All right, welcome everyone. Today's lecture 4 of 6874, etc. Today we're going to be talking about recurrent neural networks, and we're also going to have a whole section on generalization, since it's the last of the sort of formal machine learning methods before we jump into the sort of biology. We felt that it was important to sort of have some additional hints on generalization, which are going to be extremely useful for everything we saw on Tuesday with millions of parameters and everything we're seeing today with, again, possibly millions of parameters. But things that you're going to see throughout the class, you're going to need generalization. So let's talk about recurrent neural networks. I'm also surprised to see so many of you. It feels that the brain hurting that you had on Tuesday was not effective enough to read the class out. So we're going to try some more of that today. All right, so first we're going to look at how do we read. So how do we hear? How do we listen? How do we understand spoken language? As I'm going through these words, your brain is sort of masking everything out and all you're getting is concepts. But what's going on behind your brain? So in the same way that we tried to make your brain hurt last time by showing how your brain interprets images, we're now going to try to make your brain hurt by showing how your brain interprets sounds. You're going to have a hard time going through the rest of your education if you're a little more confused about all these things that you take for granted, but we're going to try anyway. So how do we read? How do we listen? How do we understand? How do we write? And also, how can machines do that? And then we're going to talk about sort of how do we encode temporal context, and then we're going to talk about sort of a very cool architecture for these recurrent neural networks, and then we're going to look at generalization. So what do you hear and why? All right, so ready for your exercises? Raise your hands who's like both frightened and excited at the same time. Yes, that's exactly how you should be feeling. All right, I want to volunteer to read the thing that I'm going to show next. Raise your hands. All right, we have one volunteer. Another volunteer. You guys are frightened. 2. All right, back there. Ready? Just read out loud what you see. 3, 2, 1. All right, so what happened here, right? So context matters. This is exactly the same character, and yet you said the cat, right? So this character and that character are exactly identical. Okay, that was easy, right? Everybody's like, oh, I should have volunteered for the first one. All right, who wants to volunteer for the second one? Raise your hands. You did awesome on the first one. Number 2. No one else? There's going to be more. They're getting harder. All right, go for it. You ready? So actually, let's get a few volunteers because there's several sentences. So you're going to read the first sentence. You're going to read the second one. You've already spoken. So anyone else? Who wants the third one? Yeah, third one. And then there's a fourth one. Who wants the fourth one? Right, one more person. All right, first. Okay, ready? Number 1. Oh, so that was top-down processing. I got this one. Don't worry, that's a freebie. Ready for the next one?
According to research at every university, it doesn't matter in what order the letters in the word are. The only important thing is that the first and last letter be at the right place.
All right, number 2.
The rest can be a total mess, and you can still read it without the problem.
Next.
This is because the human mind does not read every word by itself, but the word doesn't all.
Isn't it totally weird? Raise your hand if you could actually read this. Awesome, great. All right, I want to volunteer for the next one. I want 2 volunteers. So who had already volunteered and didn't get one? So number 4. Am I running out of volunteers here? Oh, number 4 here. And then number 5. Come on, this is not painful, right? Number 5, all right, ready? Read it out.
The message serves to prove how your mind can do amazing things.
Continue.
In the beginning, it was hard. Now, on this line, your mind is reading automatically.
All right, turns out this is a meme, okay? So, otherwise, you're going to have 7 years of bad education or something like that. All right. Oh, sorry. Who wants to do the next one? Next one? Volunteer? I think I already had a volunteer who didn't get to go. Who was it? All right, ready? Just speak out loud. Ready? Really loud. All right, how many of you actually went in your head? How many of you, you know, how do you all pronounce it, data or data? Raise your hands. This is crazy, right? How is that even possible? And then what's really cool is the survey after that. Data, data, or data, data. So context actually does matter. All right, ready for the next one? All right, listen very carefully.
The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city. The respective legislatures convening in the capital legislatures.
Okay, how many of you hear legislatures? Like you actually hear the S? Raise your hand if you can hear the S. Okay, this is.
The state governors met with their respective legislatures convening.
You hear the S, right? You hear the S. There is no S. There truly is no S. If you just look at the sounds there, there's just absolutely no S. The S completely erased. And yet, if you pay close attention, you very clearly hear the S. Listen, listen up. You hear the S. Whoops. You hear the S, right? I hear the S. I don't know what's going on in my brain, but I'm hearing the S, and there is no S. So context matters again. Your brain is basically doing a linear processing of the sound and then using that to fill in the missing information. That's exactly what we're seeing in all of these experiments, right? So, and your brain is not only using the written context or the phonetic context or sort of the, you know, transliteration of characters or the word shuffling of letters, it's also hearing lips and seeing voices, which was actually the title of this paper in 1976. You guys ready for this? That's right. So we're going to do the following. This part of the room is going to be closing their eyes. Open your ears and close your eyes completely. Not yet, but when I tell you, okay? This half is going to be looking only at the first person, okay? You can sort of put your, you know, anyway, block the others, okay? This part is going to be looking at the middle one, and this part, I'm sorry, I'm going to do it differently. You guys are going to be looking at the one closest to you, you guys at the one in the middle, you guys at the one closest to you, and you guys nothing at all. Are you guys ready? No cheating. And then I want everybody to tell me what you heard. Are you ready? Just only watch one person. All right. What did you guys hear? What did you hear? What did you hear? What did you hear? All right. So maybe this is not working so well. All right. Let's try a different segment of the video where. All right, what did you hear? All of you. Right? As soon as you close your eyes, it's a ba. As soon as you're looking, there's no b sound. Okay, again, very spooky, but let's do it again. Are you guys ready? Right? It's almost like va, va, or va, va. Va, 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 va. As soon as you close your eyes, it's ba, ba. Let's try it again. All right. It's incredible, right? You can choose when to close your eyes, and then it becomes ba. You're like, am I at MIT or in preschool? All right, so who thinks this is like totally spooky? Raise your hands if you think it's totally spooky. So your brain is messing with you. It's basically using all the information it can get from previous time, from future time, from context, from the other words, to basically fill in information. So basically inside your brain, there's actually a recurrent neural network, sorry to get so technical, that is basically floating uncertainty and evidence from past, from future, from multimodal sensing, and sort of filling in all this information, okay? In addition, every time you're speaking, the sound, by the way, who knows how you hear your own voice when you're speaking? Raise your hands. Who doesn't? Raise your hands. Okay, so it's not through your ears, it's through your bones. The way that you hear your own voice is reverberating through your bones. If you don't have experience listening to yourself recorded, as soon as you hear your recorded voice, you're like, ooh, that's weird. Is that me? That's strange. That doesn't sound like that. And the reason is because your brain is actually doing all this audio processing to sort of correct your voice to make it sound more normal, but you never actually get to hear your own voice. Okay? So there's a delay between when you actually speak and when you hear your voice. And if you change that delay by using microphones and downloading this app, this delayed auditory feedback, you will mess yourself up. You will be unable to speak. You will be unable to sort of have a conversation. And this is actually a tool that people are using in large gathering. If there's somebody who's like trying to disrupt a meeting, they're playing back their own voice with a 200 millisecond delay, and then they're unable to talk, which is very weird. Try this at home. It's fun. How many of you have actually experienced the delay when typing on your computer, either through Google Docs or through, if you're sharing your screen while on a video conference and you see a delay of your screen, so does it make you like unable to type, right? What I need to do is like close my eyes and just type away and then look, and then I see it appearing. And if it's delayed by, a second or two, no problem. But if it's delayed by, a millisecond, it totally messes you up. You can't type anymore. Okay, again, try this at home. And the whole point that I'm trying to make is, this is from just a random article that was talking about sort of how, as you're walking down the street and you hear sound, the part of your brain that is actually processing language will kick in as soon as language is detected. And then it will immediately start both interpreting and anticipating future words and sort of completing the sentence, okay? So basically, this is achieved in part by anticipating what is likely to hear. By learning what sounds signal language most frequently, the brain can predict what may come next. And during your speech processing, your brain is constantly anticipating, okay? So basically what we're gonna learn today is about how we can get machines to do that, okay? And this is kind of cool, because if a machine is just listening in, kind of like, I'm sorry, Dave, I'm afraid I can't do that. I don't know if you remember that, but the machine was reading their lips and stuff like that. So imagine a machine that's constantly listening. I don't know, kind of like Alexa at your home. It's basically doing unsupervised learning. But if you now change this machine to, instead of doing just pure listening, to try to predict the next word before it comes, it suddenly has a massive data set of supervised learning, right? It starts out as unsupervised learning, but as soon as you're trying to predict the input at t+1 based on everything up to t, and then you basically ask, how did I do? How did I do? How did I do? You basically have a self-learning machine that can learn the patterns of the human language, and it can learn to actually anticipate what you're about to type. How many of you have actually noticed, I mean, you must have, when you're typing on your phone, it basically anticipates the next word, right? It basically says, oh, you probably want to type that next. And sometimes it's right, it's kind of cool. Sometimes it's way wrong. So you can actually try just hitting the second word every time for a while and just send that message to your best friend. We'll see what happens. You could, the other thing is when you're dictating to your phone, how many of you use phone dictation? Raise your hands. Awesome, great. So I use phone dictation all the time. And as I'm looking at it, again, looking at it will distract you because there's a small delay and then will mess you up. But sometimes I manage to actually look at it when it's fast enough, and you'll actually see words going back and changing. That's because later words go back and give you more information about what that word actually was. So all of that is happening consistently inside your brain. Okay? Who's excited to find out how machines can do that? Raise your hands. Awesome. Great. So that's the goal for today. So how do we encode temporal context? How many of you have heard about HMMs before? Raise your hands. Awesome. How many of you have actually seen HMMs in a class before? Awesome. Good. How many have not? Okay. So lots of cool classes teach you about HMMs. So HMMs is one way of doing that, basically hidden Markov models. They have many, many limitations. And today we're going to learn primarily about RNNs. So basically recurrent neural networks. Okay. So first of all, how do we encode time? When applying machine learning to sequences, you want to turn an input sequence into an output sequence that lives in a different domain. So basically, very often it's going to be about word translation. Very often it's going to be a sequence of auditory signals that you're turning into speech. Very often it's going to be like individual words that you're turning into sentences, and so on and so forth. So your brain is constantly taking these sound pressures. That's all it is. It's sound pressures, and then turning them into phonemes and then words, and sometimes at the same time. So basically phonemes actually overlap in time. The end of one phoneme is well after the beginning of the next phoneme. And we do that seamlessly. And when there's no separate target sequence, you can again get a teaching signal by learning to predict the next item. So basically that blends the difference between supervised learning and unsupervised learning. So you can basically start predicting the next term and then learning about the spatial and temporal context of those sequences. So how do we do that in machine learning? It's super simple, right? All you need is to learn a set of weights. Using the same exact framework we've learned so far, you can just basically say, if I have this input at t-1 and that input at t-2, what are the weights that I'm going to have to put to predict input at time t? Right? Super, super simple. You basically have some input features and then an output feature, and you just adjust the weights. Raise your hands if you're 100% with me on this one. Awesome. Right? Any questions so far? This is actually simple. It's no magic. Okay? Alternatively, you could basically say, I have some hidden state of my mind that I'm entering right now, and that hidden state is combining multiple inputs and then predicting the next. Okay? So this is basically allowing me to now do some fancier computation. Rather than having just a linear regression or some kind of linear combination, I can now have non-linearities. I can have all kinds of other cool stuff. Is everybody with me on sort of the difference between 1 and 2? Awesome. So we can basically use a generative model with some hidden state to go beyond just simply predicting directly. And we can store this information in the hidden state for a long time. And if the dynamics are noisy, it can generate output based on a hidden state that's noisy. And in the end, you might actually never know what the hidden state was. All you know is what is the output that the model is predicting. And from that, you can infer what is the maximum a posteriori probability of the hidden state of my model. Or you could actually look at the code and sort of have debugging parameters, etc. Okay? And there's two types of hidden models that are, very commonly used. The first are linear dynamic systems, which basically drive from the input a hidden state at every point. And then that hidden state depends both on the input you're receiving at the current state and on the hidden state that you're receiving from the previous one. Okay? And then together, you're predicting an output at every point. Raise your hands if you're with me on this one. Awesome. So the hidden state can have some linear dynamics with some Gaussian noise, and then produces the observations using a linear model with some Gaussian noise. To predict the next output so that you can, I don't know, shoot down the missile or avoid a missile and stuff like that, you need to infer both the hidden state and sort of the function that predicts the output. Okay? And then you can sort of use all kinds of filters, which are analogous to the filters that we use for images, to basically choose how you're going to be combining this information across time. Why do we call them filters as opposed to just parameters? The reason we call them filters is because you're going to be using the same parameters at every time point. Okay? So the reuse of parameters happens from the fact that I'm applying a common filter i.e. a function that takes multiple inputs and gets convolved over and over and over again, okay? But now we're not convolving in space anymore, we're not convolving in time, but it's exactly the same frame. Any questions? Yeah, no? This is a non-Markovian process, yes. Any questions? Awesome. Raise your hands if you're with me. Awesome, great. So now, hidden Markov models, what do? In hidden Markov models, the input is the output. They're a generative model. They're trying to predict the observed state of the world using emission parameters based on the hidden state of the world, okay? So for those of you who haven't seen hidden Markov models before, inside here is a Markov chain. And a Markov chain is basically a series of states that you traverse from state to state. They basically have some transition probabilities from, you know, each state, states 1, 2, 3, 4, has a transition probability from 1 to 2, from 1 to 3, from 1 to 4, etc. From 2 to 1, from 2 to 2, 2 to 3, 2 to 4. So that's the Markov chain part. Every one of these boxes is a Markov chain. And across the horizontal axis is time. The cool part about hidden Markov models is that they basically tell you how to predict the next state based on the current state. And given the current state that you're in, what is the emission probability of every one of your, you know, characters that are possible in your output, okay? So basically, if you're hearing ba, 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 you basically may have b, ah, and then the b part is an utterance that has some possibility of hidden states. This might be all the possible consonants. And then the non-zero probabilities are going to be for, I don't know, v, b, and g, etc., like some consonants. And then the next one will be, you know, again, all possible phonemes as hidden states, but the ones with non-zero probabilities are probably going to be ah, okay? And then the emission is ah, or whatever you just heard. But then the cool part about these generative models is that you can use Bayes' rule to reverse the arrow of the directionality. Instead of sort of predicting, instead of generating based on this probability distribution, you can basically say, great, I have my probability distribution. I can use that probability distribution to infer the maximum a posteriori probability for each of the hidden states. Raise your hands if you're with me. Nice. Raise your hands if you're not. Okay, any questions? There's a couple of folks who are not with me, so any of you is totally allowed and welcome and encouraged to ask questions, even if you're with me. Just because you're asking a question, you might just be helping your classmates. Yes?
You can come back to the problem in the future slides.
Yeah.
You can come back in the future slides. You can explain it more about how long this relates to this.
So the whole concept of a filter is that you can apply the same function over and over again. You can have a Gaussian filter, you can have a Kalman filter, you can have all kinds of other filters. And what we're trying to do there is basically either denoise or have more emphasis on the current state and then a decay on the other states. So that's sort of where all these different families of filters come in. Does that answer your question? Any other questions? Yeah. Mm-hmm. Basically, inside an HMM, there's probabilities that basically tell you what is the probability of generating the sound from the letter A in my head, okay? That is the forward probability. It's the probability of emitting a character given my hidden state of the letter A in my head. The backward arrow basically comes from computing from the probability of emitting from the letter A to the posterior probability that the was generated by the letter A in my head. So basically you're taking a probability of B given A and you're turning into a probability of A given B times probability of B divided by probability of A. Does that make sense? So you're basically just using Bayes' rule to sort of reverse the conditional. Instead of A condition on B, you now do B condition on A. Instead of observation as in emission condition in hidden state, you basically do hidden state condition on emission. These are all great questions. Any other questions? Who feels that both questions were awesome? Yes, they are awesome. All right, any other questions? Raise your hands if you're like 100% with me here. Yeah? Okay, raise your hands if you're more than 80% with me. Nice. Okay, awesome. Good. So again, HMMs is a little parenthesis before we get to the main course. So it's like the, I don't know, amuse-gueule. All right, so you cannot be sure what state actually produced a given output. So that state is hidden. It's easy to represent the probability distribution across n states with n numbers that basically tell you what are the state transitions and what are the state emissions, the probability of emitting each character given the hidden state. And then you can predict the next output by inferring the probability distribution over hidden states. Okay, so I'm effectively equating my input to my output. The model is a generative model that basically says, well, I can generate all these characters. And then what you're saying, well, now I observed, oh, what is the most likely hidden states? Oh, it's the letter A, and so on and so forth. Okay, so that's how HMMs work. But there's limitations of HMMs. The limitation is that the only memory you have, the only state, quote unquote, you have, is where your finger is pointing at any one time. And if you want to remember, I don't know, n bits of information, you need 2 to the n possible states. Okay, it's extremely expensive. Okay, so at every time it must select one of its hidden states, and with n hidden states it can only remember log n bits about what it generated so far. And if you have information about syntax, about semantics, about accent, about the rate of speech, about volume, vocal tract characteristics, etc., you need to explode the number of states. So if you want to remember just 100 bits of information, you need 2 to the 100 hidden states. Is everybody with me so far? So that's the problem with hidden Markov models, okay? So what these recursive neural networks do is take you a step beyond that and allow you to now encode a huge amount of hidden state in your model, okay? A huge amount of state about what you've learned about the world, okay? So, and we do that all the time. Basically, you adjust utterances based on the context of the word. You adjust utterances or utterance interpretation based on the accent of the speaker, the age, the sex, the biological sex, the speed at which they're speaking, and all of that. So basically, all of these things are variables that you immediately take into account as soon as somebody starts speaking. So if you take the same sound out of context and you put it in the context of a different speaker, you will actually interpret it differently. So what do recurrent neural networks do? So basically, they combine 2 properties. On one hand, they have this hidden state, which receives information from the previous time point, and they have this input from the current time point, and they've now separated the input from the output. So I can actually train it with a very specific kind of output function. So basically, I can train it based on annotated text. Everybody with me so far? So moreover, this hidden state computation can have non-linear dynamics, which allows you to update the hidden state in much more complicated ways than hidden Markov models. With HMMs, you can only update it in some linear fashion. With RNNs, you can actually update it in much more interesting ways. And that's where all of the deep learning, all of these, sigmoid functions that we've learned about, et cetera, can come in. These ReLU functions, et cetera. Everybody with me so far? Any questions? Awesome. And with enough neurons and enough time and enough training data, RNNs can compute basically anything. They are actually a universal Turing machine. Okay, so it's kind of cool. They basically have a tape that can remember infinitely long numbers of steps. And then you can basically compute any function that's computable by computer. Okay, so be cautious because they're hugely powerful. It's like playing with a ginormous bomb when you're trying to just do simple tasks like, I don't know, understanding language. Everybody with me so far? So they're, with great power comes great responsibility. All right, everybody with me? Raise your hands if you feel like you're like, oh, there's something here that's kind of cool and I feel like I'm learning. Yeah, question.
Yeah, I'm just curious as to what are some of the tasks that a Markov model could.
It's boundless. Yeah, so the task that these recurrent neural networks can do is boundless. You can basically use it and tune it in different ways. Sorry.
Yeah, so
it's about HMNs?
Yeah, not the event of recurrent.
Yeah.
There are apps that still would be efficiently solved using the Markov model.
Oh yeah. Oh, the hidden Markov models are amazingly powerful, and you know, they've been used for language interpretation for a long time. It's just that they have this limitation about the number of states, and they have this limitation about the lack of nonlinearities. So that's why they have today been surpassed. But they were dominating the field of auditory processing for many decades before recurrent neural networks came about. So yes, they can do, you know, all of the above, but not as well. In the same way that, you know, image recognition was only done best by a, you know, neural network much late in the field, and for decades it was getting beat by all of these hand-tuned models. The same way HMMs have been dominating that field until RNNs became powerful enough and sort of parameterized enough to be able to do that. And that's only in the last few years. I mean, you guys in your lifetime have noticed how amazingly better voice recognition got. I don't know if you noticed, but all of our lectures have transcripts. Like I post a lecture and then an hour later, the lecture is processed and there's already a full transcript with closed captions. Like if you play the lectures from the last 3 times and you click on closed captions, you will actually see closed captions. It's kind of cool. The same stuff that we're teaching is actually being used in a meta kind of way to annotate our own lecture. So, you know, we're kind of in the future. Like, you should embrace that. They say that the future is here. It's just not equally distributed. Yes? It's a great question. It's a great question. When you see this arrow here, because this is such a complex model, in here, I could be storing the information about the previous state, and about the previous state, and about the previous state. So in a way, this arrow here encompasses anything that has flowed into this node. And because any amount of information can flow into that node, I could remember the entire sequence when predicting the next output. Very good question. Any other questions? Yeah. Yes. And we're going to talk about these vanishingly small gradients. Remember when we were talking about ResNet? It had like 500 layers. And by the 500th layer, it really doesn't matter what you change in your input, unless you use this residual trick of sort of flowing that information all the way up. So first we're going to, like, you're basically a little ahead on the lecture, but we're going to see that indeed these gradients are now becoming vanishingly small if you look back hundreds of steps. So we need new architectures to deal with that. And we're going to talk about that. That's where LSTMs come in, these long short memory modules. Any other questions? All right, so do they have to be stochastic? So these linear dynamic models and these hidden Markov models are stochastic. Their posterior probability distribution over the hidden state, given the observed data, is actually, however, a deterministic function of the data. So yes, there's a probability distribution, but that probability distribution you can compute perfectly given the data. In other words, there's no uncertainty as to what the probabilities are. Yes, it's probabilistic, but you can compute these probabilities deterministically. And in the same way, these recurrent neural networks are deterministic, but we can think of the hidden state of these recurrent neural networks as the equivalent of this deterministic probability distribution over the hidden states in either these linear dynamical systems or in these hidden Markov models. Okay? So the computation of that probability distribution is a deterministic computation. Raise your hand if you're with me on this one. Good. Raise your hand if your brain kind of feels like spaghetti right now. Okay, good. So we haven't hit the spaghetti stage. Everybody with me? Awesome. All right, so what behaviors can RNNs exhibit? Well, they can oscillate, which is great for, I don't know, maybe a motor control. They could settle to some attractor, which could be great for retrieving memories. They could behave chaotically, which could be bad for information processing, but it could be good for creativity. They could learn to implement lots of small programs Remember, it's a universal Turing machine. Each of which program can actually capture some nugget of knowledge and run in parallel, interacting to produce very complicated effects. For example, the RNN itself could basically choose to say, I want to remember this piece of information. It seems important. Okay? And that's something that it can do. You can basically compute functions that have these kind of choices. But the computational power of them makes them very hard to train. And for many years, you couldn't exploit this computational power. Okay? And we're going to talk about ways that we have overcome this. So I spoke about this whole concept of, yes, looking back in time across 100 time steps is kind of like in our convolutional networks going up 100 layers. Okay? That analogy is exactly what you should have in your head. Basically, this time going forward, basically this way, and sort of learning through time is exactly the same as having many, many layers that you're stacking on top of each other. Okay? So you can basically take this, recursive neural network that basically has these different states and these weights that sort of talk about these relationships, and think about all of these arrows with a +1 time delay. Okay? This node at the current time is influencing that node at the next time. And this node at the current time is influencing that node at the next time. So we don't have circularities because the model actually has a time delay incorporated into it. Okay? So if you, in fact, unroll it out in the same way that you can stack those layers, you can basically think about it as time 0 has absolutely no self edges. It just goes W1 to time 1, and then W2 to time 2, W1 to time 3, and so on and so forth. Raise your hands if you're with me on this one. Awesome. So basically, by unrolling the model from the temporal direction to this stacking direction, you can basically have a complete lack of circularity. Even though it kind of looks circular, oh, wait a minute, how am I going to estimate this? There's absolutely no circularity. It's actually super simple. You're just using the previous time point as input to the current time point. And now if you have some kind of output, some kind of input, some kind of function, you can just learn all these weights that best predict your function. Everybody with me? Awesome. All right, time for any cool questions. Yes?
So are the W1 and W3 edges of those specific for passing the knowledge down?
So these are the weights that you're learning about the relationship of those hidden units to each other. Right now, I'm only showing you hidden units. On top of that, there's a set of weights that come in from the input to the output, the loss function, etc. So you could augment all that with all kinds of additional things. But those are just weights. These are the weights that I'm learning. So if I'm trying to predict the next word in a sentence, these weights basically allow me to sort of flow information from the previous time point to the next time point to basically learn the relationship. For example, the fact that every time I see the word cat is very often preceded by the. And there would be a strong weight between the node the and the node cat, which I can sort of write as W1. Because across time, every time I see the, chances are I'm going to see cat on the next step. So that's the weight that I'm learning between those nodes. Who feels that they learned something by hearing the answer to this question? Good. So keep asking questions. They're great. All right. So there were several questions about what's being fed where and what are all these arrows doing. Okay. Let's now look at these different architectures. So what I showed you earlier was basically only looking at one hidden node and another hidden node sort of expanded in time. Okay. In particular case, I'm showing you the entire hidden state. That hidden state will be as complex as you want. Okay. It could have thousands of parameters, millions of parameters. It could basically have a node for every letter in the English language. It could have a node for every triplet of words. Sorry, for every word in the English language. It could have a node for every triplet of words in the English language, and so forth. Okay. So this hidden state could be humongous. Is everybody with me so far? Awesome. And the input is, whatever word I'm seeing at the current time point, or whatever phoneme I'm hearing, or whatever image I'm seeing as I'm driving. Okay, or the particular genomic character that I'm observing as I'm scanning through my genome, or it could be the heartbeat of a patient, or it could be thousands of variables that I'm monitoring simultaneously about a patient in the in the emergency room. Okay, in the intensive care. So basically, this is whatever data stream across many variables I'm getting at the point time point. And this hidden state is all of the state of my entire system, which could be ginormous at the current time point. Everybody with me so far? So now, this little box basically denotes a time delay. And this is just a recurrent network with no outputs. It basically simply has a hidden state that influences its next hidden state. And that's input at any time. I have the input from the current aspect from the ICU at the intensive. Raise your hands if you're with me on this diagram. And equivalent to the enrolled version of that diagram. That basically says that the previous state is influencing the current state, and that state is also influenced by no output so far. Sounds good? Yes. So sorry. It's just the time point. So basically, it's BT plus 1. It's a great question, and a lot of people are bothered by that. Let me put it this way. When you dictate into your phone, and after a while it changes, messy to, it's because it's sort of from the context inferred that this was a person we were talking about, not the phone. So the inference is yes, using information, there's no sort of there's no temporality. We're going to look at an example where as you're handwriting characters, it feels like that this character was a 3 after it sees the characters, and it goes back and forth, it doesn't know yet, and then it says, oh no, that was a 2. Okay, so yes, there's information. So, but that's because I don't have to make a prediction for it. Did everybody learn from this question? Yes. So there's 2 ways to do it. One is it could train on the spot and update the parameters of the model as you're speaking. That's one mode. The other mode is my phone has been learning from all of you guys on Google. Like, oh, I've learned from them. The normal and I'm going to predict on. Okay, so updating the model parameters can be done on a per user basis, or it can be done across the entire corpus of English language, which is a much bigger corpus. So chances are that when you're talking to your phone, it's using information from every Google user out there to basically make very good input. It's adapting it to those local patterns, but it's using information from the entire corpus of Google users. You with me? Awesome. All great questions. Keep going. No pressure. Don't worry. Even if your question is not great, I will make it great. Anybody who asked them one great question will see something great. That's such a great question. It's a great question. Well, so remember these key Markov models that we were talking about, right? It has generative arrows going forward or not in that image. We can then use those rules to infer the condition on that. Basically, all these arrows are basically saying this is the probability of B given A. But I can turn that into A given B by knowing the prior of A and the total evidence in B. Okay, so even though the arrows are unidirectional, information is flowing both ways. For example,
I don't know. Is it winter today? If I observe rain, it tells me something about whether it's winter or not. Maybe not in Boston, but in most cities, it's very important, something about the season. Causality goes the other way. It's the season that influences the weather. It's not because it's raining that suddenly it becomes spring, right? The season is the hidden state, and the observable is influenced by that hidden state. But observing that it's raining tells me something about the season. So even though the arrow of causality or of generative probabilities is pointing one way, the information can flow both ways. Learning something about this can tell me about that. Learning about that, that's what's true. Every time you see an arrow, there's information flowing through there. And it tells you about condition probabilities, about sort of how information flowing, all kinds of stuff. But arrows in general, whichever direction they're pointing, can tell you about information. But that's a great question. Any other great question? I didn't have to make a great question. All right. Sounds good? Who's with me so far? Awesome. Good. So what's the vanilla? That's level 1. Okay. Level 2 is I have a bunch of right? And I'm predicting that after the entire series of events. Basically saying, oh, or you could predict a different state. You say, and then you're like, okay, so this is one example of having a single output after the entire sequence. Okay. Predicting just one thing after the entire sequence. And then, of course, you can have some loss function that basically computes and the truth. It'll be clear if it's equals fine, and the loss function is on the out. Raise your hands if you're with me on this one. Awesome. Any questions so far? Yes.
Can I use the same approach to process images?
Absolutely. Absolutely.
Totally. Because it's just like if I transform that back into my model,
of this animal running around, and in the end I can make a prediction whether it's or not. Yeah. So, yes. So, which we created, which is awesome. If we want to make sure one graph, we should be like, oh, there's some sort of add another thing that's sort of predicting emotion, it's predicting multiple streams of information, one visual, one auditory, one about the yes. The answer to all of these questions is all you ask. All you want, how you do it from your project. Seriously, this is both society, yes. Absolutely. Other questions? Yes. I like that. It's a very good question, but I think the analogy is not as powerful because in a way, yes, as I'm staring at the image of the traverse it one way, I don't always have to traverse it that way. And the fact that I have it all temporally right there at the same time might mean something different. However, if you're thinking about an art installation, and if you're saying, oh, I wonder how people will traverse their eyes through this image, actually monitoring webcam on your computer where the users of your system are looking, then yes, you could turn a single image into a temporal information, the cursor through there. And from that, you can infer the state that the person is in, whether they're happy, if they're first looking at the dog. Does that make sense? Yeah. So again, great question. Any other questions? Okay. Awesome. So we saw a very simple model, just a hidden state, no output, but then so a hidden state, an output, and a target, and a loss function. I could basically have my output sort of not just at the last step, but at every step. Maybe what I've annotated is, maybe you guys want to write a voice recognition system as your final project. And what you could do is take the input stream of the recorded videos from this lecture and the output stream of the transcript you already produced for the same lecture. That is target Y at every point, right? So the output Y could be the transcript of the input and visual at the current time point. Okay, so you could be target and at one system generating every time point. And then of course the loss function comparing with it. Raise your hands if you're with me on this one. Awesome. Sounds good? And again, sort of now the shooting state only points to itself. I'm only flowing information from the previous state. Let's make this one. I can basically flow information to the next hidden state. So instead of linking up my network this way with all of my hidden states pointing to each other and receiving input from the previous hidden state, the input of this hidden state are here and here. Instead, I could actually have them be from the output of the previous hidden. Okay? Everybody with me on this one? Because maybe I don't need to sort of encode this massive state as an input. What I care about is whether I predict the right thing or not, or whether I predict it or not. Okay? So basically now, the next state only receives information about what I'm currently observing and the fact that I predicted the job at the previous time. Everybody with me here? There's a challenge, of course, which is that when I'm training this model, I cannot simply parallelize the training. I cannot simply run all time points at the same time. The reason for that is that I have to observe something, which basically means I have to predict something before I feed it into my network. Can everybody see that? Awesome. Yes. You're pointing to the next picture. Okay. But basically, what you were just saying is, wait a minute, why do I have to take as input whatever I predicted? Why don't I take as input whatever the ground truth was? Right? So as an input, I could feed it the target. Everybody sees that? And that's exactly what this is. 1 second. Instead of basically feeding the hidden state to the hidden state, again, I have to infer from the data, therefore I have to train sequentially. I can just feed two things to the next state. I can feed the current input and the ground truth target Y from the previous state. Everybody with me? So at training time, I can just give it both the output Y and the input X. And at test time, I could basically say, all right, well, how am I doing? How is my output matching the previous input? Everybody with me on this one? I have questions. So, Right. Oh, yeah. Sorry. So yes, for both this one and that one, I cannot just train a compiler. Correct. Correct. Basically, I can't train on the labels because there's no input like that. Correct. So basically, this one I can train massively parallel. This one I have to train sequentially. Yes.
Training on the actual observation and training. Does that work? Because then when I test, as in that picture, I don't have actual labels.
Yeah. So you do because you're using whatever just happened as an input. This is also training, not in the output. Okay, so this is also training. Don't think that this is not training. This is using the output which I'm trying to match to the target. Okay, but this one at runtime will receive an input which is the previous answer, and therefore when I'm running it even in real time, I get all the input I have from the previous. Great question. Yeah.
For the feature forcing, it's like you have the actual prediction.
It's saying that at every point I'm forcing it to see from the training from the feature. They're all useful for different things. Just exposing you to a large set of possible architectures so that you're aware of them, but like in practice, just try them out. Any other questions? Yes. The fact that I'm reusing my parameters at every layer. So in this network, like in this feed-forward network, as I unroll time now on the stacks, at every layer I have the opportunity to learn a different function. Whereas now I'm forced to use the same function from T-1 to T-1 as I'm using from T-1 to T. But every layer is learning the exact same parameter set. I have coupled the parameters across every one of the layers. Does that answer your question? Or you could reinforce it, you could just hammer it into some artificial setup where it's exactly the same, but you're still, constrained by the fact that these parameters are coupled. Like you could make a CNN look like an RNN, but you can't make an RNN look like a CNN. Basically, a CNN, this convolutional neural network, has the expressive capacity as a different way that. Whereas here we can't. But you could have parameter coupling in your CNN. You have all the same parameters everywhere, and then it'll just look like an RNN. Any other questions? Who said that they need a 30-second stretch break? Mandatory. Or we're going to stand up. Stealing calories from your next lecture. Ha ha ha. There be mine. Yeah. All right. Ready, guys? Let's do it. All right, raise your hands if you feel like you've learned stuff so far. Do you feel like you've learned stuff? Yeah, that's great. Awesome. All right, so what we've seen is this very powerful approach basically learn pictures through have an outline there. But now we need to actually learn these parameters, right? So by now, parameters, we're going to number basically going to be doing back-propagation through time. Okay, so basically our back-propagation will be asking how is this W here affected by this change here and this change there. I'm going to be basically going through back-propagation. Okay, so the model is predicting forward in time. So change. I have to make some small change here. What I want to know now is how much closer can I get my Y, sorry, my O to my Y by updating my W and my V given everything that I've seen so far. Of these delta W of L divided by delta V, right? So the partial derivative of a loss function relative to my weight across every back time step. Raise your hands if you're with me. Nice. Very good. So, linear constraints between the weight. We compute the gradient as usual, and then modify the gradient so that it's going to satisfy the gradient function. The delta of our loss function, the delta for our weights, and then we can constrain them to be the same across all time steps. So, you know, you don't have to take the derivative separately between the weight. You can actually couple the weight. And you have to delta anything, you know, relative to W. You instead feed it delta A relative to W1 and W2. That's how you do model coupling. Every single time, if I start with the same weight vectors, and if my partial derivatives are always coupled, I will update them always together, and then these will stay the same. Is everybody with me so far? So now as I'm doing this backprop, I'm reusing all of my W's over and over and over again. But I'm forcing them to basically be a single gradient. Raise your hand if you're with me. Nice. Question.
So in that, when you use
Sound good? So if it's only now I'm forcing all of the ways to be the same, and the way that I'm doing that in the combination. So you can think of it as a layered forward network with shared weights, and then for net with those weight constraints. In the forward pass, you could build a stack of activities across all the units at every point there. In the backward pass, you this at all the different times. Ready with me? So you can apply this learning to sequences. You want to have an input sequence and output sequence. They might live in different domains. I might be translating, you know, utterances into characters. I might be translating phonemes into syllables. I might be translating English into French or into Chinese. Anything goes. Basically, anything that's temporal in one space could be translated to temporal in another space. Like you could be watching a video and then annotating the scenes that you're saying, or going from one domain to another domain. Do you know that one? There's no separate target sequence. You can see and the model that learns how the world functions, our videos and then what will happen next is that the ball will keep on falling faster and faster. You learn the notion of gravity by watching videos. Ready with me? And then predicts the next term of the second sequence of words at the function. So this is all nice and sweet, but we now have hundreds and potentially thousands of time points. In an hour and a half lecture, you have a bazillion little milliseconds that you can go through. How do you do learning through these hugely vanishing small? How do you remember stuff that you've learned for longer periods? One, which is what we're going to use mostly, what's the most widely used, is long short-term memory. So you basically make the neural network with little modules that are designed to remember values for a long time. Another one is a very cool sort of technique that is widely with a tiny gradient and tiny. So, you know, it's the optimizer. Basically, you trick your hidden state to amplify itself to basically sort of create an echo that will at every single time reinforce itself. Initialize there is a reservoir of weakly coupled oscillators that can be selectively driven by the people. So this echo feedback turn the hidden out. You could also use a momentum in the initialization to basically trick your echo state network to sort of get into that state of remembering. The most widely used of all is really the long short-term memory. This is just awesomely cool. This was actually developed in '97 to solve the problem of getting this recurrent neural network to remember things for a long time, like hundreds of steps. And they designed a memory cell using both logistic and linear units with multiplicative interactions. So when the right gate is on, it stays still as long as the peak gate is on, and it's still by turning on the wait gate. So by the learning model itself, it can be like, oh, this is important, I'm going to remember it. And oh, I need this anymore. Okay, so here's what this looks like. You basically have your input from the rest of the CNN. Everybody with me on this arrow? We have the output to the rest of the CNN, of the RNN, just like we saw before. And you have the hidden to hidden information, just as we saw before. Everybody with me on those three? These three are unchanged. The only thing that changes is that you now have these gates that are choosing whether I'm going to write, whether I'm going to read, and whether I'm going to. Raise your hands if you're with me. Raise your hands if you kind of see that this is kind of cool. Okay? And what's really cool is that the network itself is controlling whether it needs to remember something. Self-remember, which chooses as part of the learning algorithm how to control these gates and when to turn them on and off.
Dog that starts to run, it's remembering the dog until the dog, I'm sorry, is like goes off to heaven. And then you don't have to remember the dog anymore. It's like, oh, I can sort of shut off the memory of the dog. Okay? All the dogs will always stay in our hearts forever. Everybody with me here? So basically you have a linear unit with a self-link with a weight of 1 that basically allows that memory to be propagated forever as long as the keep gate is on. Okay? And then you store information by activating the right gate. Shoop, I've stored something. The little dog is there. I'm remembering the doggy. And then shoop, dog is off. Okay? So I have some input. I turn on the right gate. I'm now remembering the input. I've turned off the keep, so I've forgotten whatever I had before. Now only doggy is in my heart. Okay? And then I'm not reading doggy yet. And then I keep going. I'm remembering doggy 100%. Dog is not decaying. Doggy is 100% remembered at every single time point, okay? I'm not writing anything, I'm just keeping doggy with me. And then I can decide to read doggy, and then keep goes to 0, right? As long as keep is 1, there's no decay in my memory. So I can remember things forever. Is everybody with me? Yes? Yeah, you could be reading while you're writing. You could be combining these two inputs, like there's a little cat and a doggy and they go together, you know, etc. Everybody with me? Awesome. All right, so this is the coolest thing. And this is basically how every RNN nowadays is working. Because of this vanishingly small gradients problem. This completely solves that problem by basically enabling you to both remember things forever and also choose when to remember, choose when to keep remembering, and choose when to forget. Sounds good? Raise your hands if you think this is kind of cool. Yay, awesome. All right, so now you can use it to do all kinds of cool stuff. You can basically read cursive writing. And there's a little video that you can play, you know, that basically shows you how, as the pen is going through this, you're sort of recognizing different characters. It shows you how it's sometimes waiting to recognize that this was an A until some time after the A was written, and how it's remembering the past by activating the units that are currently being remembered. So you can see this memory, for example, has been kept, even though these other memories have been erased. Right? So that's an LSTM at work. So click on this and you will play. Everybody with me? Awesome. There's the problem with initialization, of course, how to deal with the boundary cases. You need to specify the initial activity state of all of the hidden and the output units. You could just fix these initial states to have some default value, but it's better to treat them as learned parameters. And you can adjust these initial states by following the same gradient, okay? So you're basically learning through, and then you can sort of adjust these accordingly. And then sort of there's this forward pass where you're squashing all of these inputs to prevent the activity effects from exploding. And in this backward pass, which is completely linear, and then you're sort of using these derivatives. And then, yeah, we talked about all that. All right. So what we've basically learned is how you can read, listen, understand, and write by using context information, by sort of flowing in information. How you can encode this temporal context using either hidden Markov models that basically have a very limited amount of state, or using these recurrent neural networks that have a huge amount of state. And how there's this challenge of these vanishingly small gradients as you're going through hundreds of time steps, thousands of time steps, and a very cool module that allows you to sort of overcome this. Okay, any other remaining questions? Who feels that they've learned a ton of stuff today? Awesome. I could cover the rest of the material in 2 minutes, but I think I'm going to save it for a future lecture. It's a good idea? Yeah? All right, awesome. So you guys are dismissed early. This is awesome. 2 more minutes of your day.